Thank you everyone for attending. My name is Dr. Ahsan Naim, and I'm representing Anspec Technologies. And the topic of my presentation today is boosting 5G NR cell capacity with a simple firmware update. I think you saw Tracy. I was speaking with her earlier today, and I explained her what we are doing. And she had a comment on this title. She said I should replace 5G with XG because it's agnostic. I mean, we're demonstrating that this works on 5G, but we have already established that it works on 4G, and hopefully it will work on 6G also. All right, so let me go to the next slide. What is the biggest issue that network operators are facing today? Any takers? Cost, right? Like a flat ARPU, but they need to meet the ever increasing data demand, right? Traffic volume is exploding, and based on some recent projections, is increasing at the rate of 25% CAGR, which means it roughly doubles every 3 years. So they need to add capacity to keep pace with the growing data demand, right? That's a big challenge. And spectrum scarcity, right? I'm not sure if you're following what AT&T paid roughly $23 billion to EchoStar, it was probably a couple of weeks ago or something like that. So the operator is spending billions of dollars. I believe Verizon spent more than $50 billion on C-band spectrum auction a few years ago. So you need more capacity. Spectrum is very expensive. And the other options like, massive MIMO deployments, cell densification, they're all expensive. It takes several years to build a macro site. So it's not that easy. So operators need the capacity today, but there's no easy solutions out there, right? So our approach, in which it's a common theme among some of the operators in terms of their vision for 6G, is that it needs to be a software-based solution, right? Same hardware, a software upgrade, right? So this is what our approach is, that the technology that we have developed in Anspec, it's a software-based solution, and it can help the operators install base, and they can increase the capacity of the network by a simple software or firmware update, right? All right. I know, Zishan, you have experience in RF, right? So let's make it interactive, right? This is typically what happens in a cellular network. You have users that gets like 1 bar if they are like indoors in the basement, in elevators, right? And then you have users that basically get full 5 bars, right? So here in this slide, I'm showing this with the help of some concentric circles. The yellow circle, which is the outmost circle, represents users that are at the cell edge, and typically they would get the most conservative modulation scheme like QPSK, right? And that means that they will be carrying just 2 bits per symbol, right? And on the other extreme end, you have users that have full 5 bars, right? And they are getting 256 QAM, highest modulation possible in 5G in downlink, and carrying 8 bits per symbol, right? So, but from scheduler point of view, the scheduler or the base station needs to serve everyone, right? So there are resources which are shown here in yellow that gets allocated to QPSK user. They transmit 2 bits, and then on the other hand, you have 256 QAM users transmitting 8 bits, right? So it's not from the G-Node point of view, it's not most efficient to provide 2 bits per symbol, right? But it really is dictated by the channel conditions. So due to scheduler fairness, there is an impact on the overall throughput of the system, right? In the ideal world, if the maximization of the throughput is the main main focus of the scheduler, all the resources would be allocated to 256 QAM users, right? But then that would cause resource starvation for the QPSK user. So because of this, we have this idle strong users. Like for the resources that gets allocated to QPSK type users, 256 QAM or other strong channel users are basically sitting idle. They're not getting resources allocated, right? So that creates a bottleneck effect. And this is how we define the average spectral efficiency. Basically, it's a weighted average of the users in a busy hour. You have QPSK, you have 16 QAM, you have 64 QAM, 256 QAM users, and then based on the resources that gets allocated, you take a weighted average of it. And this becomes, this serves as a baseline capacity for a 5G network, right? It's different from a peak speed, but because peak speed is ideal, means like excellent RF conditions, in reality, that doesn't happen, right? So in the busy hour, this is what an operator typically sees in the network, right? So here you see 4 different modulation schemes that I was referring to in the previous slides, right? Starting from QPSK to 256 QAM. What do you see here between like all 4? What is the pattern here between like in 256 QAM, QPSK? Any comment on that? What is the difference between these 4 constellations? Yes, yes. But in the constellation, you see 256 is most crowded, right? And because of that, you transmit more bits. And QPSK is less crowded, right? It just only has 4 points, right? But then the penalty is that you're only transmitting 2 bits per symbol, right? So what we are doing in NSPEC is that we are exploiting this constellation space that you see here in QPSK. You have much more space available in signals space, right? So we are exploiting this. And what we do is we pair a weak channel user with a strong channel user. So I want you to focus on the figure on the left. You have on the top, you have a standard 4G or 5G. You have a weak channel user, and you have a strong channel user, and the resources get allocated to each user, right? And you can see that in blue, the weak channel user has low data downloaded, and then the strong channel user transmits more data, right? And then the scheduler needs to split resources. So in this particular case, if we have a fairness scheduling, then 50% of the resources will be allocated to the strong channel user, and then the remaining 50% will be to the weak channel user. With our NSPEC enhancement, what happens is that we don't do any modifications during the transmission of the strong channel user because it's already operating at capacity, right? 8 bits per symbol. But during the transmissions of the weak channel user, which is the QPSK in this case, we piggyback some extra data that is intended for the strong channel user. And then the signal remains, the entire operation remains completely transparent from the QPSK or weak channel point of view, right? So the weak channel user doesn't even see any difference. It decodes its signal in a normal manner. Whereas the strong channel user gets some extra data opportunistically. So this piggybacking, transparent piggybacking, results in increase in the spectral efficiency, capacity of the network. And the good thing about this is completely software-based. There's no requirement for any additional spectrum or hardware change. All right. So how this works? Basically, at the scheduler level, when there is a weak channel user and the scheduler is allocating resources to that user, we pair that weak channel user with a strong channel user. And then instead of transmitting, let's say, a regular QPSK, we transmit a constellation that we call it as a shared constellation. And that constellation looks or appears as a regular QPSK constellation for the weak channel, but then it is also carrying some data for the strong channel. So at the decoder side, for the weak channel, QPSK user decodes his data in a normal manner, and then the strong channel user also extracts its own transparent piggyback bits. And this is how we achieve the capacity gain. Let me give you an example here. Let's assume that you have two users in the network. A simple case, this is what we were showing. A modified version of this is what we are demonstrating in our demo here. So you have two users, and 50% of the resources are allocated to 256 QAM, which is shown here with these red rectangles. And then you have these yellow rectangles, which represents 50% of the resources allocated to the QPSK user, right? So in this particular case, the 256 QAM user gets 4 additional bits. And using the formula that we discussed a couple of slides ago, which is for the average spectral efficiency, we see that now in this case, for the 50% of the resources allocated to the strong channel user, it's the same 8 bits per symbol, whereas for the remaining 50% of the resources, it's 2 bits plus the 4 additional bits. The 4 additional bits are intended for the 256 QAM user. So this results in a 40% throughput gain for this simple 2-user scenario, right? Now you'll ask that in reality, you don't have 2 users. In a busy hour, you have 10s, 20s, or even 50s of users, and they'll have a distribution. Some of them are in QPSK, some are in 16 QAM, some have MCSs that are tied to 64 QAM and 256 QAM, right? So what does the capacity look like in a real cellular system, right? So here, we're using an MCS distribution that is based on a benchmark study of an AT&T's network in Indianapolis that was conducted in 2017. And you can see here that roughly 29.6% PRBs are allocated to QPSK user. You have roughly 29% to 16 QAM, then similarly 34.4% to 64 QAM users, and then less than 7% PRBs are allocated to the 256 QAM. So if we use this distribution and then assume that for QPSK users we transmit 4 extra bits, for the 16 QAM users we transmit 2 extra bits, and then for the 64 QAM users we transmit 1 additional bits, exploiting the concept of pairing a weak channel user with a strong channel user. This results in 64.5% capacity gain, right? So in reality, it will vary because every cell has a different distribution. It varies from one time to another time. So the gain we expect is going to vary from 40 to 60%. It could be higher also, but it again is a function of the distribution of MCS in a cell. All right. So this slide talks about the prototype, the demo that we were showing earlier today and yesterday. So this test bed is an end-to-end 5G network. For core, we are using Open 5GS. And then for base station, we are using srsRAN, G-Node B with 5-layer modifications. That's where we tweak the code to implement our technology. And then in terms of hardware, we are using B210s as a front end. And then we are using 2 handsets. One is Xiaomi 12 handset that has Snapdragon chipset from Qualcomm. And then the second user is the srsUE's user. And then the Xiaomi handset is playing a role of a weak channel user. So we have, in this setup, we fixed that MCS to MCS5, which is basically QPSK. And the setup runs a 10 megahertz FDD carrier, and we are allocating 100% resources, which is all 52 PRBs to this COTS UE Xiaomi 12, and it is getting roughly, I think, close to 5 megabits per second. That's based on the standard because this is working in the single input, single output mode, so there's no MIMO here. And then we have a strong channel user, which is our own srsRAN open source 5G user that's also getting this 5 megabits per second. So this is acting as a strong channel user. So we are basically demonstrating that we are able to double the throughput here. So instead of the two users splitting the total 5 megabits of capacity available, each of them are getting 5 megabits, so it's 100% boost in the capacity. And this has zero impact to the weak channel user, Xiaomi 12, and Xiaomi 12 has the Snapdragon chipset, so that basically proves that entire operation is 5G standards compliant. So why this is important? Again, the main thing is that a huge capacity boost, 40 to 60% boost in the average cell capacity. And again, it's 100% software-based implementation. It is applicable to multi-generations. It can work with 4G, 5G, and in future 6G. Because the changes are happening at the modulation level. So all these four modulations are likely to be used in the 6G standards also. And this is also applicable to Wi-Fi and even cable. As long as you're using QAMs and you have a system where you have weak channel and strong channels, so this disparity can be exploited by our technology to achieve a boost in the network capacity. And it's completely transparent operation. So the legacy user in the previous slide, which was Xiaomi COTS, doesn't need to have any firmware updates. So it works with the legacy systems. And then one other thing is that since this technology works at the modulation mapper level, so it's completely agnostic to what is going on at the physical layer. So at the physical layer, it could be TDD, it could be FDD, could be doing spatial multiplexing, beamforming. So all the benefits can be stacked up because this is exploiting a totally different dimension in our technology. And then it can be easily integrated with ORAN systems, and even with proprietary vendor stacks that are not ORAN compliant. So from deployment and licensing point of view, what our vision is basically that for the existing user base, the operator can ask its own vendor to basically implement this technology via firmware update at the G node Bs, the base stations, and similarly can also ask the handset vendors to do the same, a simple firmware update. The firmware update at the handset side is very simple. For this entire technology, 95% roughly of the intelligence is happening at the G node B side. So there's a very simple, minor firmware update that is required at the handset side. All right, so that's pretty much it. Any questions? Absolutely. Go ahead.
Very interesting idea after you and very talk. This is going to open a new dimension when you're scheduling the users at the MAC layer, right? Did you do any work in user scheduling?
So based on our experience, we want to keep things as simple as possible, right? There's definitely ways where fancy type of algorithms can be implemented, but what we feel is that even today, the scheduler at the TTI level knows how many users needs to be served, what are the MCSs, right? And as long as scheduler can find a weak channel user and a strong channel user, meaning like the MCS that are tied to different modulation schemes, MCS 5, let's say, and then there are MCS 12, which is a 16 QAM user, depending on which table in the 3GPP user, right? It can be paired. So it's very easy that, as the scheduler already has that information available, it has the profile of, what MCSs are currently tied to the users that have the data ready to be transmitted. So it's just a matter of simply pairing. But again, we can do fancy things to even increase the capacity. But even today, without making any changes in the scheduler, as long as the scheduler is capable of pairing the strong channel user with weak channel user, we can make that happen. But let me add one thing here, that the more disparity there is between the pair, the more the gain is. Like, if you're pairing a QPSK user with a 16 QAM, you're not going to get that much capacity boost, but you'll get a great capacity boost if a QPSK user gets paired with 256 QAM, right? You saw that it's like 4 extra bits. So in essence, it's a 200% boost for that particular resources, right? So whereas roughly would be 50% boost if you pair a QPSK with a 16 QAM. So these um, kind of aspects need to be still taken into consideration. But again, all the information is already available at the scheduler in the standard 5G operations. A scheduler knows what the MCS profile of the users are. Yeah. Yes. So it's a great question. So we think in terms of the 16 QAM, QPSK, 16 QAM, right, 64 QAM, 256 QAM, right? But in general, you could say that weak signal, moderate signal, strong signal regions, right? So these are semantics, right? Uh, as long as there is a disparity in the signal strength, and then you have users that have different MCSs that are tied to different modulation schemes, we can use that, right? So for example, uh, a weak channel user can be a 16 QAM user, and then a strong channel user can be in a 256 QAM, right? So you can also pair them, these two together. One user can be in 16 QAM, another can be in 64 QAM, right? So as long as they are operating at different modulation levels, right, modulation schemes, these can be they can be paired, and then you can get the capacity gain, right? So it will work for all the different regions. The exception is that an extreme scenario where you have no disparity. Let's say all users are in QPSK, or right. So then there won't be any benefit, right? Because there's no disparity to be exploited. Or if all the users happen to be in a very strong signal condition like 256 QAM, then again, the extreme scenario, there is no capacity gain. But we all know that in a busy hour, especially, there is a distribution, and then you have users that are in good channel conditions, bad channel conditions. So as long as there is a disparity, this can be exploited. Yes. Sure. So, sure. Absolutely. Got it. So I'm using these MCS 256 QAM or as an analogy, right? That's a strong channel versus a weak channel, right? So what is happening is that we transmit a signal that appears like a QPSK signal to the QPSK user. Okay, but the same signal, when received by a user that has a very high signal to noise ratio, like as a normal like 256 QAM user, that signal will appear or will be received by the strong channel user as as something different. It's not going to be a standard QPSK signal, right? So that user can extract some extra bits from that signal that we transmit in our NSPEC technology implementation, right? So think of it as that you have one same signal, but based on your signal strength or signal to noise ratio, it's perceived differently by different users. You have QPSK, it will appear like as if it's a regular QPSK signal, but if you are a strong channel user, it will appear as something where you can go and extract some extra bits, transparently.
Are we not asking sometimes of your asking your front-end here, asking directly the vendor for the high value of the open source is fine. But commercial content, commercial scenario, you're asking the operators to change your spectrum.
Yes. That's an excellent question. So the whole point of using this, and then we're thankful to srsRAN that they have provided a platform that can be used to implement this technology, right? So the whole idea is we're not building a product. We're demonstrating that through srsRAN stack that this technology can be implemented on a 5G, on a network running 5G standards protocols. And then can get the GIS capacity boost, right? So the operators can ask their own vendors to get this implemented, right? So because what we have done is in the srsRAN may not be applicable to the firmware or the software stack of the operator's vendor, right? So it's proprietary implementation. They are in the best position to implement this. But what we are demonstrating here is that technology can be implemented on a 5G network without breaking the standards. Oh yeah, please go ahead.
Yes, thank you for the presentation. I'm Yoshi from SoftBank. Okay, so from also the network operator perspective, I think this technology would be very useful for the increasing capacity. If I remember correctly, I saw similar technology discussed in 3GPP, which was NOMA, non-orthogonal multiple access. And then at the time, 3GPP took the long discussions and then decided not to standardize this technology in the 3GPP specification. So, but then this can be implemented in the network side like a DU. And I also think that this is feasible technology from map layer perspective. But then the point would be the UE side. I mean that in this technology, UE need or SIC. SIC is a successive interference cancellation. So that was one reason that 3GPP excluded this technology in the standard. So nowadays, I think that the UE implement very good hardware, good software. So that I think SIC may be feasible technology in a commercial field. From that perspective, do you think that the 5G UE can implement SIC on this technology?
Great question. So yes, you're right that I think it was release 14, if I'm not mistaken, MUST, multi-user superposition transmission, is the variant of NOMA that got implemented, right? Or at least it's standardized. And then you pointed out that you require SIC, and that's probably the reason why this did not get implemented, right? Because the handsets They are sensitive, doesn't have that much power capacity, right, to have these extra processing. So this looks similar to NOMA, but the main difference is that in this technology, we don't need any SIC. Yes, that's the thing. And, the SIC, for those who may not have the background, will be, should be implemented at the receiver side. So that's why the gentleman was referring to, the handset side, right? And that's has, some penalties in terms of power consumption, right? So first of all, we don't need that. And there's no SIC required here. And also, 95% of the intelligence is in the G node B side, and only 5% is there's a very simple tweak that we had to do in the UE side, for which we're thankful to srsRAN for providing in this OpenStack for SRS UE. That it's literally like less than 50 lines of codes overall, that we had to change to make this implemented. So short answer is that I think it will be challenging because there are so many constraints as far as the handsets are concerned. But the beauty of this technology is that no SIC required, simple firmware update, and can be easily implemented. And that firmware changes that we are talking about can be easily updated over the year, firmware updates. So, yeah.
I will run study this. Different.
Well, thank you. I don't think we have any more questions, right? Okay. Thank you. Thank you, everyone.